Hello. In this video, we are going to be looking at waves, specifically light waves, looking at their characteristics, and then talking about how chemists use those characteristics. So first of all, if we're talking about light, we need to remember that light is part of the electromagnetic spectrum, or the EM spectrum as I like to call it. The EM spectrum has many different types of radiation. You all saw this in Integrated Science 9, but this will be a quick refresher. So the EM spectrum has waves from radio waves, which are our longest types of waves, all the way up to gamma rays, which are the shortest but most intense types of waves. The visible light is only a small portion of that EM spectrum. The other types of waves we cannot see, whereas visible light we can see. All of those waves are similar in that they travel in waves. Now waves, here you can see, maybe get a visual for the EM spectrum. You've probably seen this, like I said before, in Integrated Science 9 class. So this is separated by wavelength, frequency, type of radiation. Our longest wavelengths would be over here, our radio waves, getting smaller and smaller and smaller to our shortest wavelengths over here, our gamma rays. Again, those are our most intense or our highest frequency waves. We have X-rays, ultraviolet, infrared, microwave in between. And then again, we are going to be mainly concerned with this visible spectrum here, going from violet down to our longest types of waves, our red waves. So again, focusing on that visible light spectrum. So some characteristics of waves that you need to know. You should already know these, but a quick review. So wavelength, that is the distance between identical points on a wave. So those identical points could be the crest or the peaks. They could also be the troughs. Essentially, wavelengths are just the length of one full wave. You can think about it as like your stride length is the distance between your feet when you take a stride. Wavelength is the distance of one full wave. Now frequency, we represent that with the letter V. This is a number of waves that pass a particular point in 1 second of time. So if they're traveling really fast, if there's that high intensity, those gamma rays, those are going to have a really high frequency, whereas the radio waves, much lower frequency. Finally, amplitude. This is the vertical distance from the midline of a wave to the top or to the bottom of the trough. So either one. And here's kind of a visual for you guys. These are 3 different waves that you can compare. Here we've got a longer wave. So this is wave A. Its wavelength is longer. However, its frequency is shorter. So you can tell that there are fewer waves that occur in that same amount of time. Whereas wave B, shorter wavelengths, higher frequency, we were getting more waves that pass in a given amount of time. Finally, wave C, even a shorter wavelength and a higher frequency. And then amplitude, the midline to the peak, or you could also measure it midline to the trough and you get the same thing. So you should recognize that these properties are mathematically related by this equation. C, representing our speed of light, is equal to the frequency times our wavelength. Okay, now a couple important things to note. So you need to know C, this is a constant, this is the speed of light, 2.99 times 10 to the 8th. Guys, go ahead and round that up to 3 times 10 to the 8th. It'll make your life simpler. 3 times 10 to the 8th, and then the units here are meters per second. So if you have one of your variables in meters per second, the other 2 variables have to be in those same units. So our wavelength then is in meters, frequency in S-1, so it's like the inverse of seconds, so 1 over seconds. All right, so you need to know those characteristics because you're going to use these characteristics to do a few calculations. So here's our first calculation. The wavelength of a laser pointer is reported to be 663 nanometers. What is the frequency of this light? So I would go ahead and circle. Okay, here is something important, 663 nanometers. That's important. We're going to need to know that. The question that it's asking us to solve is frequency. So maybe put like a little question mark here on top of frequency. That's what we're looking for. All right, so here's how we're going to solve it. first we have to rearrange that equation and solve for frequency. Okay, so we just rearranged that and got V equals C over lambda. So our speed of light divided by our wavelength. Now, also very important, I told you that it had to be in the correct units. So 663 nanometers, we have to convert that to meters, okay? So 1 nanometer is 10 to the negative 9th meters. When you do that conversion, when you multiply those, you're going to get 6.63 times 10 to the negative 7th meters. Okay, so now our wavelength is in meters, our speed of light, and you can see rounded here, 3 times 10 to the 8th meters per second, divided by our wavelength, 6.63 times 10 to the negative 7th meters, is going to give us a frequency of 4.52 times 10 to the 14th per second. So what that number means, we're getting 4.52 times 10 to the 14th waves per second. So pretty high frequency. Okay, here's your turn. Calculate the wavelength of light in nanometers with a frequency of 3.52 times 10 to the 14th waves per second. All right, so a little bit of advice. You're going to have to take this equation and solve it in terms of lambda, and solve it like that be in terms of your wavelength. So should use equation C divided by V. Don't forget your C, that's a constant. It never changes, 3 times 10 to the 8th. Your wavelength is already in the proper unit, so you should be able to plug and chug there. Should get this number, 852 nanometers. All right, let's keep going. So why are we talking about this now? Well, we're talking about this because we've just finished talking about ions and how ions can become excited. Well, they have a really special property when they become excited, when they come to that ionic state, and that they have more energy. So this was discovered by in the 1900s by Max Planck. He discovered that radiant energy could only be emitted or absorbed in discrete quantities, meaning very small packets of energy. He did this with a black body experiment, and it was huge. It kind of, like I said, revolutionized way of thinking for how energy is in smaller pockets. Okay, so he developed an equation that relates energy to frequency of a wave. Okay, so you need to write this down. You need to know these variables. E representing energy in joules. H is going to be Planck's constant. So another constant for you, 6.63 times 10 to the negative 34th joule seconds. And then V, we know, is our frequency of that wave. So you need to know these 3 variables because you will have to use them in our lab to do some calculations. So let's do an example calculation together. We're going to skip over some of that. So calculate the energy of a photon. A photon is that packet of light energy that has a wavelength of 700 nanometers. All right, so important things to note if you're annotating this. Energy is what we're looking for. So our question that we're trying to solve for is energy. Our units then, if we're looking for energy, should be in units of joules. Another thing that's important is our wavelength, 700 nanometers. Okay, so again, we've got to convert 700 nanometers to meters in order to do this. And just remember that conversion, 10 to the negative 9th meters is 1 nanometer. Your units here will cancel, leaving you with 7 times 10 to the negative 7th meters. Our frequency, what we're doing here is we're saying, okay, well, we don't know our frequency because we were given the wavelength of light. But if you remember a couple examples ago, to get our frequency, we took the speed of light, that 3 times 10 to the negative 8th, divided it by our wavelength, and got a frequency of 4.29 times 10 to the 14th. We can take this answer then and plug it into that equation I just taught you, that H being Planck's constant times frequency, and we'll get that the energy is 2.84 times 10 to the negative 19th joules. Okay, so I know that was a lot. That was like a 4-step problem, but it just shows you how these characteristics are all related. You know, if you were asked to calculate energy, but you're given wavelength, we can still do that because of our first characteristic, C is equal to lambda V, calculating our wavelength here, or our frequency here, I mean, in that second step. Then we can use that information to calculate the energy of that photon. So here's another example problem, your turn. Calculate the wavelength of light with this energy, 7.85 times 10 to the negative 19th joule per photon. In what region of the EM radiation does this light fall? So important things. We're given the wavelengths, or we're given the energy, and we're asked to calculate wavelength. So essentially, we're doing this whole process in reverse, okay? So the first thing we'll do is calculate the frequency. We'll use the frequency to calculate wavelength, and then we'll look at our chart and figure out, well, where on the EM spectrum does that fall, okay? So here we go. Here we are calculating our frequency. We are taking that energy divided by Planck's constant, and we got our frequency. Here we're using our first equation, speed of light divided by our frequency, giving us our wavelength of 253 nanometers. And if you go back to our region, our EM spectrum, where are you? Here we go. 253 nanometers. Let's see, should be in the ultraviolet. So as you notice here, we're getting smaller and smaller and smaller on our wavelength. So it would be right after the 400, the violet section. So it should be somewhere close to the ultraviolet section. All right, so this concludes the first set of notes and I wanted to talk to you guys about as far as waves, wave properties. There's going to be a second video next that will explain what we are doing in this lab. Thank you.